Hello everyone, welcome back to ptet.chemistry channel. So in this restructured format of full paper tutorials, I'll cover this November 2020. This is 9701 paper 1-2. So this is a multiple choice paper 1-2. As per the new restructured format, I no longer show the question paper because I'm afraid of breaching copyright issues. So you know where to get your your question paper. I've already mentioned the subject code as well as the paper code. So if you know where to get the paper, then you will know what I'm talking about. So in this first question, they're asking for the average oxidation number. So if you have average oxidation number, this is a skill that was probably first learned when you were in IGCSE or O-level chemistry. The first compound given there is this calcium hydrogen sulfide. So we know that calcium is a group 2 metal. So we have calcium 2 plus, and we can imagine that we have 2 of these thing, which is Y, let's say. So 2Y is going to be 0. If I just take the charge on the calcium, which is plus 2, so 2Y is equal to minus 2, Y equal to minus 1. So we can imagine that as being HSO3 minus, or obviously you can see it, 2 of the HSO3 minus, they will balance out the charge of 1 calcium 2 plus. Now, what is the oxidation state of the sulfur here? We can imagine now that this is a minus 1 charge. So you can either do it from the overall compound, or you can do it in terms of the ion. I'll show it in terms of the ion first. Minus 1 equal to the charge of the hydrogen. The oxidation state of hydrogen, the compound is plus 1. You have 1 hydrogen, and the sulfur is unknown. And you got 3 oxygen. Each of them will have oxidation state of minus 2 because it's oxygen in the compound. So sulfur then is going to be, this is plus 1, minus 6 is going to be minus 5. Move the minus 5 to the other side, you will get minus 1 plus 5. This is sulfur plus 4. If you decide, however, to start from here, then the overall compound is 0 oxidation state because compound doesn't have any charge. You can do calcium as plus 2, and then you will have plus 2 in the big bracket because you got 2 of that species. And you get hydrogen, which is plus 1, sulfur, which is unknown, and 3 times minus 2 for the 3 oxygen. And it's a similar kind of story. So what I have in the bracket there is plus 1 minus 5. Minus 6 is going to give you minus 5, so sulfur minus 5. If you just move sulfur minus 5, keep it on the right hand side, then you move minus 2 to the other side. And then you have 2 times this. 2 can go down there as divide. So that is going to give you 2 divided by 2, which is minus 1. So sulfur equal to minus 1 plus 5. Sulfur equal to plus 4. As you can see, they are the exact same answer. Whether you start from the compound oxidation state or you start from the ion oxidation state, they're going to end up with the same answer. Alright, so if I just jump on straight onto the second part, which is the second molecule given there. Well, second compound, not a molecule. So if I just do using the overall oxidation state as 0, and I've got 2 sodium. Sodium is in group 1, so it's a plus 1 oxidation state. I've got 2 sulfur, and I've got 3 oxygen. Then 0 equal to plus 2, minus 6 is minus 4. Plus 2 minus 6 is minus 4, so it's 2 sulfur minus 4. And that's going to give me 2 sulfur equal to plus 4. Sulfur equal to plus 4 over 2. This gives me sulfur plus 2. So we have plus 4 for the first one and plus 2 for the second one. This is going to be option A as your answer there. In the next question 2, so this is a mole calculation. Is it a mole calculation? Nah, it's a percentage composition by mass. Alright, so this is called percentage composition by mass kind of question. So this all contains 4% by mass of MnO2, and they say no other manganese compound. So there's nothing else that contain manganese, which means all the manganese are within the MnO2. But of course, they want the excuse me, they want the mass of manganese. Therefore, we still need to consider out of the MnO2 how much of it is manganese. All right, how much of that is actually manganese? How much is actually manganese? And that is what you want. You want the mass of manganese that will be obtained from 1 tons of the ore. Okay, so this is a question of percentage out of percentage out of the whole thing really. Okay, so if I just start off by calculating the MR of MnO2, because that is how you work out the percentage composition, you got to divide by the MR of that substance. So from the data booklet, you can get 86.9 if you do the correct adding up the relative atomic masses from the periodic table. So in the second part, what you will get is you will get mass of manganese in MnO2 is going to be how many manganese do you have? You have one manganese. Each manganese is 54.9 relative atomic mass divided by the overall 86.9. That is the mass of manganese in that MnO2. Actually, it's the fraction of it. I shouldn't say in the MnO2. I should really say in the ore itself. So I know how much manganese is in here now, but out of the ore, there's only 4%. So it's 4% out of 1 tons. So out of the ore, only 4% is MnO2. Out of MnO2, how many of it is actually Mn over the whole MR of that MnO2 within the ore? Okay, so once you set it up, it's just pressing your calculator and you can get this to be 0.02527 tons. But none of the answers are given in tons, they are in kilogram. So 1, 2, and 3, you multiply by 1,000 and you get 25.27 kilogram to 3 significant figure as the data shown in the question here. So this is the 3 significant figure. So 25.3 kilo is going to be option A there. Question 3, so what do we have? They're asking for atom of phosphorus. So if you look from the periodic table, you will know that this is a period 3 because it's in the third row of the periodic table, is in group 5. Well, you don't use the Roman numeral in A level, you use group 15, but you know it has got 5 valence electrons, and that's why it's in group 15 there. Okay, in terms of the electronic configuration, it's going to be 1s2, 2s2, 2p3, 3s2, 3p3. It's the third element in the p block because it's group 15. Across the third period, you fill the 3s with 2 electrons first, and then your remaining electrons will be 3 out of that 5 valence electrons that you have. So which atomic orbitals are occupied? Well, if I look at option A, B, C, and D, I can see A is definitely wrong because of one thing. This is the one that is wrong. You don't have 1p. And then in terms of B, what is wrong is the 2D. The 2D is definitely wrong because you don't have 2D. And then between C and D, well, between C and D, I can tell C must be the answer because I'll show you why D cannot be the answer right now. So you have 2p, 3s, and 3d. We can see that fill up to here, and you don't feel the 3D at all. So you don't feel the 3D at all, not feel for phosphorus. So D cannot be the answer. C is the only answer there. Okay. Moving on to question 4. So the structure of compound A is shown there. I think it's probably best if I draw it out because there's almost no way of me explaining this with words unless I actually, am crazy just to describe with words. I am just drawing a molecule here. Okay, so the molecule I could have gotten from anywhere. The molecule does not belong to anyone. The structure, of course, can be obtained from the internet. So this is what they say is compound A. So some of the carbon atoms are tetrahedral. So we know tetrahedral is a geometry. Tetrahedral geometry is a result of 4 bonding pair of electrons and 0 lone pair of electrons. The 4 bond pair of electrons repel equally, and that's your valence shell electron pair repulsion theory. They say candidates should be able to state and explain the shape in terms of electron pair repulsion theory. They also said that some of the other carbon atoms are trigonoplanar. There's going to be 3 bond pair and 0 lone pair. The 3 bond pair repel equally again, so they give you your trigonoplanar geometry. I'm just going to very quickly talk about hybridization. In terms of 4 plus 0, you're going to get 4 electron pair. In terms of 4 electron pair, your carbon has to use the 2s orbital for bonding. So there is one of the 2s And how many of the P does it have to combine with the S and mix together to give you 4? You got 1 plus 3. That's why it's carbon sp3. That's associated with a tetrahedral carbon and 109 degree. On the other hand, if you got trigonoplanar geometry, 3 plus 0 give you 3 electron pair. So that will give you carbon sp. 2 because 1 plus something give you 3 electron pairs. Electron pair is a result of adding up the bond pair and the lone pair. So there's carbon sp2 that's associated with trigonoplanar 120 degree carbon geometry there. So they're looking for how many carbon atom of each type. So if I just highlight this with green and the other one, let's say I highlight it with brown. So let me go and look for tetrahedral carbon. So green one, tetrahedral carbon 1 there, 2 there, 3 there, 4, 5, 6, 7, 8, well, 7, 8, there's a bit clearer, 9, alright, so we're looking for carbon bonded to 4 covalent, well, forming 4 covalent bond, which is 4 sigma bond, 1, 2, 3, 4, I don't show the hydrogen, but there's actually 4 covalent bonds on this carbon, not just 4 covalent bond, 4 single covalent bond, meaning 4 sigma bond, which is the bond pair there. Okay, so I don't go for the one with the double bonds because that will be the pi bond. All right, so that is where you have trigonoplanar geometry. All right, so I'm gonna do the carbon sp2 now, which is trigonoplanar 1, 2, and then 3 there, 4 there, 5 there, 6, 7, 8, and I've got 8 trigonoplanar, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of that, hang on, let me just change the color first. So I've got 9 of that carbon sp3, and I've got sp2, which is the brown color one. I've got 8 of them. This is going to give me option D as the correct answer there. So knowing how to read the diagram and not just what is shown, but also what is not shown very clearly is very important. So in question 5, we have a mixture. We have a mixture of magnesium oxide and aluminium oxide. This looks complicated. Why does it look complicated? Okay, never mind. We are given 2 equations there. Aluminium oxide reacting with hydroxide, giving us this soluble ion. This is a white. Well, this is a solid that doesn't dissolve in water. It's pH 7 in water because it's insoluble in water. It's a period 3 oxide as part of your case study in AS Inorganic Chemistry. It can react with hydroxide because it's an amphoteric oxide. It can react with both acid as well as base. This is a colorless solution because it dissolves, just like aluminium hydroxide dissolve in aqueous hydroxide to give you a colorless solution. Alright, so there's 2 other equations that they have shown you. One of them is just Al2O3 reacting with acid, giving you that. What other information do we have? Let me just finish copying this down first. So it takes a bit more effort without the question being shown to you, but you know, you have the question paper in front of you, so yeah, consider yourself lucky, I guess. Anyway, so what do we know? We know that 100 cm cube of 2 molar NaOH, so 100 cm cube of 2 mol per dm cube NaOH is enough to dissolve X gram of the mixture. Hang on, X gram is not aluminium oxide because X gram refers to this one as well as this one. So this and this together is X gram of the mixture. But then we know that HCl only reacts with Al2O3 as well as MgO, but the hydroxide does not react with MgO because MgO is a basic oxide, so it doesn't react with OH minus. Al2O3 is amphoteric oxide, so it reacts with both base as well as acid. So this is a reaction just with acid, and they say that with HCl, you're gonna need 800 cm cube of 2 mol per dm cube HCl. They will react with both of these in 2 separate reactions, whereas this is all the sodium hydroxide that's needed for that. I am thinking that I should do some mole calculations. Perhaps I can get started. Um, okay, what can I do? Maybe the mole of NaOH first. The mole of NaOH is going to be CV, concentration in mole per dm cube, times volume in dm cube. So make sure you know that you're doing the correct unit. So 100 times 10 to the minus 3 means 100 divided by 1000 to convert cm cube to dm cube. That will give me 0.2 mole. So I get 0.2 mole of OH minus. I know how many mole of Al2O3 therefore. From that first equation, the mole of Al2O3 over the mole of hydroxide. From the equation, if you have watched my other videos, you know that I'm a big fan of setting up my mole ratio like this, because I get to see very clearly, and across all my mole calculation I always do this kind of method. Whether you like it or not is up to you. Whether you've seen it and then you feel like you want to try it, you really have to try it with your own examples, and the more examples you do with this method, the better you get at it. It's not learned by just watching. Once you learn something, especially with calculations or math, you have to actually put into practice and you know, practice it. Okay, so I have put down Al2O3 on top, so I need to read the equation. I've got 1 Al2O3 give me 2 hydroxide. Based on what I have labeled, 1 Al2O3 give me 2 hydroxide. There's the mole ratio, and now I gotta put in the actual mole of the Al2O3 that actually reacted with this much mole of the sodium hydroxide. So there's 0.2 mole down there. So the actual mole, I should have N to represent the mole, is going to be, this brings up 0.2 divided by 2, which is 0.1 mole. So now I know I have 0.1 mole of Al2O3. The question now is, okay, so if I know how much Al2O3 I have in separate reactions in the mixture, then I can work out the mole of the acid required. If I know the total acid that I reacted with, then if I know the acid that reacted with Al2O3 here, that means I can work out the mole of acid here, and therefore I can work out the mole of MgO here. Alright, so I hope that makes sense there. The fact that I've got 0.1 mole for aluminum oxide, this means I can cross out option A. Option B must be incorrect based on my first mole calculation. So I'm left with option C or D as the possible answer. We have already worked out the mole of Al2O3, and that means I can work out the mole of acid that reacted with this. I know the total mole of acid added, because CV will give me the total mole of acid reacted, minus the mole of acid reacted with Al2O3. Then I can get the mole of acid here. If I know the mole of acid here, I can get the mole of MgO that reacted with this much acid, and there will be our answer there. So that's the trick there. Okay, let's see, what can I do? So the total, okay, I work out the total mole first. Okay, the mole of HCl used, total mole of HCl used, N equal to CV, so 800 divided by 1000 times 2 mole per dm cube. And put that into your calculator, and you will get 1.6 mole. From your balance equation, you require 6 mole of acid to Al2O3. So the mole of H plus, well, in fact, the mole of HCl. So HCl, 1 HCl give you 1 H plus, the mole of HCl to the mole of Al2O3. From that equation involving the acid, 6 acid is to 1 Al2O3. 6 acid is to 1 Al2O3. So the mole of acid reacted there relative to the mole of the Al2O3, which is 0.1. So the mole of the acid is going to be 6 times 0.1, which is 0.6 mole. This is the mole of acid reacted with Al2O3. If that is true, therefore the mole of HCl reacted with MgO, like we said, is the total mole of our acid minus however mole of acid that has reacted only with Al2O3. So 1.6 minus 0.6 is 1.0 mole. This is the mole of HCl that reacted with MgO. So if I know the mole of HCl here, I can work out the mole of MgO that are in this reaction. Okay, so 1 mole of MgO to 2 mole of acid. 1 MgO is to 2 acid. So the mole of MgO is to the mole of acid. 1 MgO is to 2 mole of acid. I want the actual mole of MgO. That is my final piece in this MCQ question. Put 1.0 down there. I'm starting to run out of space at the bottom there, so I'm just using let me think if I can move some stuff up there. I think I can, because I don't want to write too much to the bottom. Okay, I might be able to squeeze in the line there. So the actual mole of MgO is going to be 1.0 divided by 2, 0.50 mole, which means altogether I have 0.10 mole Al2O3 and 0.50 mole of MgO. That is going to be option D as the only correct answer there. Question 6. What do we have in question 6? We have a graph of PV against T. This looks like ideal gas question. So what do we know about ideal gas equation? PV equal to nRT. PV equal to nRT. So PV against T. PV against T. So this N and R is a constant, because fixed mass of gas, so the mass is not changing, the MR is not changing, so N is not changing. R is a molar gas constant, so that's just going to be a constant. So PV equal to constant times T. So PV is your Y, this is your X, this is your M, so which means it's going to be a gradient. So this is the gradient, so it's a straight line plot, and that's why you are seeing a straight line plot which is looking pretty much like did I draw that right? Let me see. Let me try and get right as much as I can. So it looks like a straight line plot, PV against T, so the gradient is just M there. Anyway, so which gas give this graph over the widest range of temperature? Give this graph. This graph assumes ideal gas behavior. So the one that will give you this graph over the largest range of temperature means as ideal as possible. You want it to be as ideal as possible. So we're looking at the most ideal gas. The key here is the most ideal gas. So you want the least or the weakest intermolecular force. So out of hydrogen, HCl, HF and O2, we can be thinking about van der Waals. Van der Waals, yes. You can be thinking about permanent dipoles. H2 is non-polar, HCl, HF is polar. And in terms of hydrogen bond, only the HF can form hydrogen bond then, because of the very electronegative or fluorine atom there. So this is going to be the least ideal. Second least ideal is going to be HCl, because at least it is polar. So between H2 and O2, which are non-polar because they have the atoms of the same electronegativity, so you call them non-polar. So how do you decide in terms of their van der Waals? You want the weakest van der Waals, because only 2 electrons in the molecule, whereas oxygen has you got 2 oxygen, which is 2 times 8 protons, so you got 16 protons, and it's a molecule with no charge. Therefore, the total number of electrons equal to the total number of protons. So this one is stronger van der Waals due to more total number of electrons in the molecule. That's why A is the correct answer, and none of the other one is the correct answer for this graph to be as ideal as possible over the widest range of temperature as well as pressure. Question 7. Question 7 is about, well, it's an ideal gas question again, all right? So when we have PV equal to nRT, we want the volume correct to 3 sig figs. So volume equal to, we're given masses. So perhaps I should convert the mole into mass. So mass of a mR times RT. Make V the subject first. I'm not a big fan of putting in values first, then you'll be wasting your time. You should always rearrange the equation. Then later on you just put them in when you work out what are the correct unit there. The M there must be in gram. So at the moment it's 12.0 kilogram. Kilogram times 10 to the 3 means times 1,000. We'll change that into gram. My MR is going to be, well, actually I should probably settle the one on top first. So R is equal to 8.31. 8.31 from the data booklet. So it's actually joule per Kelvin per mole. And then that temperature must be in Kelvin, and already given to you in Kelvin, so that's all right. And pressure is 6,000 Pascal, which is already Newton per meter square, so that one is all right as well. Your MR of helium is a noble gas, so it's monoatomic. They do not form molecule at all. They exist as single atom, so that is just 4 from the data booklet, 4 gram per mole. You sub all of that into your calculator, and you're gonna get volume as 897.48 meter cube. Now we have an issue because all the answer given to us is in dm cube, so all the answer in dm cube. So the 3 significant figure is not the important, it's not quite important here, but then we need to convert it into dm cube because this is the standard unit as per the ideal gas equation. So we got to be thinking about how to convert meter cube to dm cube. So some students will memorize this, some teachers would ask the student to memorize it. I personally always show the student how to get it because I never memorized this. So I know that 1 meter is equal to 100 cm, and I know that 10 cm equal to 1 dm. So decimeter means 10, so 1 dm is 10 cm, so 100 cm means 10 dm. All right, so therefore 1 meter is equal to 10 dm, because you can imagine that when you have 100 cm is equal to 10 dm. So if 1 meter equal to 100 cm and 100 cm equal to 10 dm, so 1 meter equal to 10 dm. All right, so that's just the way I think, and it might not be your favorite way of thinking, but at the very least, you know, I can get what I want. So we want meter cube, so whatever we do on the left, we have to do it on the right. And in having said that, 1 cube is 1, meter cube is meter cube, 10 cube is going to be 1000, that's going to give me dm cube. So how do I convert meter cube to dm cube? I just multiply by 10 to the 3. So what is that going to give me? Let me see. So therefore, the volume is 897.48 times 10 to the 3 dm cube. And that means I'll get 897.480 meter cube, dm cube, and convert that to 3 significant figure. So 897.000 dm cube to 3 significant figure. That's going to be option C. Option C is the correct answer there. Question 8. So which pair of enthalpy changes will always share the same sign? Always share the same sign, meaning both are always exothermic. Okay, always same sign. So they are kind enough to interpret the question to you, i.e. both lesser than 0 or both greater than 0. This is going to be endothermic. This is going to be exothermic. So let's try and think about each of the option here. So enthalpy of atomization, the sign, is this a good one to do? Well, okay, let me just do it. Enthalpy of atomization is always greater than 0, whereas enthalpy of neutralization is always going to be lesser than 0. Here, you're forming gaseous atom from its elements in standard states. So, you know, forming gaseous atom always require energy. Neutralization is basically H plus OH minus. You are not breaking anything. You are just forming covalent bond. Between the H plus and OH minus, you're forming a new covalent bond. It's always going to be exothermic. So A cannot be the answer. They have totally different sign then. In terms of B, atomization again is always going to be endothermic, but enthalpy of solution can be lesser than 0 or greater than 0. So, you know, when it's lesser than 0, most likely is soluble. So we are not saying that the thing will definitely be soluble if it is exothermic, but it's most likely going to be soluble, and this is going to be insoluble most likely if the enthalpy of solution is endothermic. And this is related to something that you will learn in A2 energetics as Gibbs enthalpy change. All right, it'll make more sense in A2. So again, they have different sign. They don't have always the same sign. So B cannot be the answer there. In terms of C, we have enthalpy of combustion is always lesser than 0. Enthalpy of combustion is always less than 0. Enthalpy of hydration is defined as when you take 1 mole of the gaseous ion and then you surround it with, you dissolve it in a large amount of water. So you are surrounding, whether you have metal cation, you're surrounding it with the water, which is polar. So it's going to be surrounded by the delta minus oxygen because this is cationic metal ion. So it doesn't matter whether you have metal ion or non-metal ion, you know, it's always going to be exothermic, because if you have anion, then what's going to happen is it will be the hydrogen end, which is delta plus, they will be attracted or surrounding the X minus like that. All right, so regardless, it's still going to be exothermic because you take 1 mole of the gaseous ion very far apart with no forces attraction, and then you bring them and surround them with water, and you're forming this thing called ion dipole bond. Ion because you have a full cation or anion. Dipole because water molecule is polar. So this is the ion dipole bond. Gaseous ions very far apart with no interaction whatsoever. And then you're forming bond is going to be exothermic. Here you can see they have the same sign. This is definitely the answer that you're looking for, because if you check option D, based on what we have said earlier about enthalpy of solution, it can be greater than 0 or lesser than 0, so meaning it can be plus minus sign, whereas enthalpy of hydration is always lesser than 0, meaning it's always a negative sign because it can only be exothermic based on what we have said about the formation of ion dipole bond. Moving on to the next question, which is question 9. So what do we have here? We have 2ClO2 plus 2OH minus. Oops, sorry, it's an error. Going to ClO2 minus plus ClO3 minus plus H2O. This is the question about oxidation and reduction. So if we just work out the oxidation state of the chlorine here, this is a compound with no charge. So we don't care about the number in front. We just look at one formula unit when we do oxidation number. The overall compound is obviously uncharged, so it's 0. Chlorine is what I want to find. Each oxygen is going to be -2 because it's oxygen in a compound. That's why it has oxidation state of -2, which is the charge that that atom will carry if it does form an ion. So Cl is going to be +4 there. And here, the oxygen again is -2. The hydrogen is +1. I should really focus or at least mention something about the oxygen being -2 there. And we have an ion here. This is no longer ClO2, it's ClO2 minus. So the oxidation state of the oxygen is -2, which means if I have -1 overall oxidation state because it's an ion, equal to chlorine plus 2 times -1. Chlorine equal to -1 plus, plus 2. Nope, that's not correct because each oxygen is -2. No wonder I look confused. So it's going to be chlorine equal to -1 plus 4, chlorine equal to +3 there. In terms of ClO3 minus, you got the oxygen to be -2, you got -1 to be the overall charge, which means the overall charge of the ion is the oxidation state of the ion. The chlorine is the unknown, and you got 3 oxygen now, 3 times -2. Chlorine is -1 plus 6, chlorine is +5 there. This is water molecule, this is hydrogen +1, oxygen -2, +1 plus 1 plus 2, -2 times 1, overall oxidation state 0 there. So what can we say there? There is literally no change in the oxygen oxidation number. There is no change in the oxygen oxidation number. So when it says some oxygen atoms are oxidized, you can definitely cross out D. Option D is wrong. Oxygen all -2 there. Okay, so oxygen atoms are reduced, oxygen atoms are oxidized. You can cross out A and you can cross out B as well. Okay, which means really there's only option C, and we can see why that is. The chlorine +4, if I just circle it, chlorine +4 going to chlorine +3, this is a decrease in oxidation number. This is called reduction. If I use another color, this is chlorine +5. So chlorine +4 going to chlorine +5 is an increase in oxidation number. This is what you call oxidation. We can see one chlorine species has both been oxidized and reduced in the same reaction. This is a type of reaction you would call this disproportionation. So in structured questions, they usually ask you define disproportionation. What do you understand by disproportionation? A redox reaction where one species is both oxidized and reduced in the same reaction. In the next question, so this is question 10. So this looks like, well, it's a Kp kind of calculation. So 2s2 gas plus O2 gas in equilibrium, giving you 2SO3 gas. So, oh, they are very kind. They have already given you partial pressure. So I think this is a pretty straightforward question. The partial pressure is given as kilopascal. The SO2 is the unknown here. The O2 is already given as 375. The SO3 is given as 20.3. All of them are in kilopascal. That's why the answer are also in kilopascal. So Kp, the value of which is given next to the equilibrium equations. I wouldn't write it down. You have it on your paper. If you set up the expression, so Kp is to do with partial pressure of the substance on the right, and then you got to raise it up to the power based on the balance equation. So it's partial pressure SO3 square divided by partial pressure of SO2 square, because there are two SO2 in the balance equation, multiplied by the partial pressure O2. The product appear on the right hand side, the reactant appear on the left hand side, and this is going to be, what do you want actually? You want PSO3. Nope, you want PSO2 because you want the partial pressure SO2. So you want this thing. So I'm going to rearrange it. SO2 square equal to SO3 square there, divided by Kp times partial pressure of O2. I think you can see then the square has to go into a square root on the other side. So if I just copy this whole thing, at this stage you can probably put in the value straight away already. It's just a lot easier if I just show you now, but at that stage really it's just a matter of putting in the value and you can go home nice and happy. So partial pressure SO3 is 20.3 square, and then divided by Kp. The value of Kp is 2.96 times 10 to the minus 9. And then you have partial pressure of O2, which is 375. So my square root looks a bit small there. And I got 375. And yeah, I mean, just press your calculator. Make sure that you should do the thing in the bracket first before you press the square root. So a lot of students, they decided to, do everything in one go, which is all right if you're very good at using bracket. If you're very careless at using bracket, you really should do the thing in the bracket first, and then when you get a final answer, you square root the answer, and then you should be able to get partial pressure SO2 at 609,304.7 Pascal. And am I correct? Oh, I think I know why I did what I did wrong already. Okay, now there's a mistake here because I did say it wasn't important. It is actually very important because we're gonna read this very carefully. Pascal minus 1. This is Pascal minus 1. What have I done? This is kilopascal. By right, what I should do is I should convert this to Pascal in order to use this. So let's convert this to Pascal instead of kilopascal. So let me change that. So this is a mistake. If I change this to Pascal, then I'll have 10 to the 3. Then I'll multiply this by 10 to the 3, which means I have to put in 10 to the 3 and 10 to the 3, which means this x will be obtained in Pascal as well. Even though the answer is in kilopascal, I'll get the answer in Pascal to match the Kp unit, and then I can convert to kilopascal in my final step. All right, so remember this times 10 to the 3. So I've got to change that. So this is times 10 to the 3, and then the whole thing square. So it's not as easy as it seems now, all right? So, there's probably where they're trying to catch the students out. And there is there a square there? No, there's no square there because this is the partial pressure of oxygen. This is the partial pressure of SO3. So do the thing in the bracket first. And I'll draw my square root once again. Okay, so I convert that to Pascal. This one will be in Pascal. And then I will get my SO2 partial pressure, put it into a calculator, and you get 609,304.7. This is in Pascal because the unit of the Kp that I used was in Pascal minus 1. Okay, So I got to convert this back to kilopascal because the option given in the question is in kilopascal. So I gotta have 60123, so divide by 1000 in order to convert back to kilopascal. You can of course do this on your calculator. By all means do that just to get the correct answer to 3 significant figure. This is actually option B. To make sure that you can get to the correct answer, you can convert this to Pascal, which is 609000, and then you put that into this expression here, and you should get Kp equal to whatever Kp value that they give you in the question in Pascal -1. Okay, that's how you check your answer will be correct. Probably best to speed out a little bit. Question 11. So we have Haber process. The key thing here really is about rate. So rate is the key thing here, not equilibrium or equilibrium position or equilibrium yield. Equilibrium yield. So not all of that stuff. It's just about rate. So talking about removing ammonia or talking about decreasing temperature. Well, actually decreasing temperature can do a couple of things, but yeah, I mean the only thing that can increase the rate, we can think about temperature. Temperature increase is good for rate. These are gaseous reaction. So gaseous reactions, if you increase pressure, they can collide, the reacting particles can collide more frequently. So collision frequency will increase because there are more particles per unit area. So that means rate will increase. So temperature decreasing, which is option B, is not going to give you higher rate, although it will give you more equilibrium product because the forward reaction is exothermic. But this question is about rate and not equilibrium. So realistically speaking, we are talking about pressure. So there's option C, very, very straightforward there. Okay. Question 12. So what do we have in question 12? We have element X, which is a period 3 element. So period 3 chemistry is part of your AS inorganic chemistry. We're talking about oxide. So the oxide is giant structure. Be careful. They don't say it's giant ionic or giant molecular. So it could be giant ionic. It could also be giant molecular or giant covalent, whichever one you like. What it cannot be is it cannot be giant metallic because it's an oxide, so it's an element. It's not an element, it's a compound, so it cannot be giant metallic. All right. So looking at the option, phosphorus oxide is definitely out because P4O6, P4O10, they are simple molecular or simple covalent structure. Okay, so you can cross out option D, which means you're left between A, B, and C. Now, the second information is covalent bond with chlorine. Covalent bond with chlorine. Well, I can think about SiCl4, which is this tetrahedral molecule. Tetrahedral molecule because it is simple molecular with a tetrahedral geometry 109 degree. I can also be thinking about Al2Cl6, which is basically a dimer of AlCl3, where you can dimerize to give you Al2Cl6 as a result of incompletely filled outer shell. So instead what you get is you get this in the gaseous phase. So I always like to draw the display form like this first, and then you can get the dot and cross very easily. So two of them are dative covalent bond. They are like inverse partners, this donating to this and this donating to that. And that obviously rule out magnesium chloride, which is giant ionic structure. So that is going to be ionic and not covalent, which means it cannot be option A there. And then in terms of the oxide can neutralize HCl, so Al2O3 and SiO2. SiO2 is an acidic oxide. You use it to react with calcium oxide as a way to remove, is it calcium oxide? Sorry, you react it with calcium oxide in your extraction of iron. This is from your IGCSE or your O-level chemistry. You react SiO2 with calcium oxide and you get calcium silicate. It's called SLAG, S-L-A-G. All right. Al2O3 on the other hand is amphoteric oxide. Amphoteric oxide mean it can react with both acid and bases. This is similar to one of the earlier question where we talk about aluminum oxide reacting with hydroxide, which is a base or alkali, as well as an acid, which was the HCl in that calculation question. So this thing, no reaction with HCl, meaning to say we can cross out option C, and therefore we are left with option B, which is the correct answer for question 12. Question 13, so this is a chemistry of barium, color seen when you burn it in oxygen, that is going to give you a green flame. There is the barium metal burning in oxygen, there's green flame, and the pH, well, we know the barium hydroxide, the pH is around 14, well here is 13, and then the pH of magnesium hydroxide is going to be around 9. This is your chemistry of MgO dissolved in water. So this is a weak base because it reversibly dissociates into OH minus, so not a lot of OH minus. In fact, going down group 2, so going down group 2, I know I'm going against the trend, but you know, I'm trying my best to actually write it down that from magnesium to barium, the group 2 hydroxide become more soluble. That is why you get more OH minus in solution. That's why the pH becomes more and more alkaline. So in conjunction with, in association, I guess, with the color seen, which is the green flame, as well as you have the pH 13 or pH 14, which is very strong base. There's just option B as your answer. Very straightforward there. Question 14. So question 14 is about some qualitative analysis, am I correct? Looks like it's a test for halide ion. We have a Ag plus aqueous, plus X minus aqueous, reversible to give us this reaction. This is actually a precipitation reaction because aqueous solution plus aqueous solution giving you the silver halide solid, which is a precipitate. And then you have equilibrium 2, where the Ag plus aqueous reacts with 2NH3. This is something that you will learn more in A2 under transition metal chemistry. But in fact, this is basically a big part of AS organic chemistry. This is an ingredient for Tollens reagent. Tollens reagent is the test for aldehyde, and it will give you silver mirror as this thing get reduced. Ag plus 1 because NH3 have no charge at all, so it's Ag plus 1 and then plus 0, overall charge become plus 1 there. So it's silver 1 get reduced to silver 0. That's why you get the silver mirror as the positive test when aldehyde is present, because you can oxidize aldehyde itself get reduced to give you silver mirror there. So that is your equilibrium 2, and this is aqueous. Is also the product that you get when you try and dissolve silver chloride in excess aqueous ammonia. It does dissolve, the white precipitate dissolve to give you a colorless solution. All right. So which statement is correct? They are looking for correct statement. If you look at option A, so what does option A says? Option A says position of equilibrium 1 lies to the left. Equilibrium 1 lies to the left when X minus is equal to I minus. So we know that AgI is very insoluble. So that means AgX a solid, AgI precipitate out. So the AgI is a yellow solid. As you form the solid, more and more of it will replace the right hand side in order to form more and more solid. Therefore, that is actually wrong. The equilibrium will shift to the right as more and more I minus react. Okay, so A cannot be correct. In terms of B is about concentration of ammonia for equilibrium 1. Equilibrium 2 can affect equilibrium 1. So if you look at equilibrium 2 first of all, what happened when NH3 concentration increase? When NH3 concentration increase, the equilibrium will try to remove the extra NH3. It will react with the NH3 and goes this way, so it will shift this equilibrium 2 to the right. So that means your Ag plus will decrease as equilibrium 2 shift to the right hand side. And if your Ag plus decrease in concentration, so that means equilibrium 1, when you have lesser of these, equilibrium will shift this way in order to increase the concentration of Ag plus. All right, so they are interrelated here. As this increase, this will decrease because it will react with more of these to form these, and because this one decrease, so equilibrium 1 will try to produce more of these in order to boost to return the concentration Ag plus back in equilibrium. So this equilibrium 1 will shift backward, and that is exactly what it says. So therefore equilibrium 1 tries to increase the concentration of Ag plus. This is how you explain it in terms of Le Chatelier principle if this is in a structured paper. So equilibrium 1 shift to the left. So I already gotten the answer. I should be able to move on. Let me see if I can just very quickly explain why C and D is incorrect. So it says Kc for equilibrium 2 is larger. Equilibrium 2 is about dissolving the well, basically forming this complex, whether it's soluble or not. We know that AgI is definitely insoluble, which means AgI doesn't dissolve in excess NH3 to give you this at all, because it doesn't favor that way. AgI definitely favor this way, AgCl favor this way. So when x minus equal to Cl minus, Kc for equilibrium 2 is larger. Is that correct? Let me see. Equilibrium 2. But equilibrium 2 has no AgCl. I beg your pardon, okay? Equilibrium 2 has no AgCl. If you have Cl minus versus I minus will form the precipitate more favorably. Therefore you have lesser Ag plus. If you have lesser Ag plus, this equilibrium, what am I talking about? Let me paraphrase that. Let me think about this. Equilibrium 2. I would actually imagine that if for equilibrium 2, it's actually quite hard to tell whether the Kc will be larger or not, because both the chloride and the iodide will try and precipitate out the silver halide, and both of them will therefore use up the Ag plus, and therefore both of them will actually have this equilibrium shifting this way in order to produce more Ag plus as you precipitate out. So I can't really say Kc is definitely larger or smaller. I think definitely option B is the correct one compared to option C. So you know, when you're dealing with MCQ, you gotta think about which one is the easier one to justify, and in this case option B is definitely easier to justify, and I'll probably just move on from there. But then if you look at equilibrium, option D, they say equilibrium 2 is a redox, and that is completely wrong, because equilibrium 2 is not a redox. If you look at the oxidation state, this is silver plus 1, and then remember the NH3 has no charge, so that means Ag is still plus 1, because plus 1 and no charge give you overall plus 1. So this must be silver plus 1, which means there is no change in oxidation number. So talking about it being redox is definitely completely wrong. We are just looking at option B as the only possible, definitely the easier one to check the correct option for question 14 there. Question 15, so we have water and ammonia. So what do we know? We know that ammonia dissociates in water reversibly or partially to give you the hydroxide ion. That is basically the definition of a weak base, which is reversible dissociation or partial ionization or partial dissociation in water in order to give you a hydroxide ion. So what statement is correct? This is called ammonium ion. So a lot of students always get confused between ammonia as well as ammonium. So it's important not to, be distracted by all these things. If you draw the shape of it, because there's one of the things that's being asked there. Nitrogen is in group 15. It's got 5 valence electron. It uses 3 for forming covalent bond. So it still has 1 more lone pair. So 3 bond pair and 1 lone pair. This is what you call trigonal pyramidal. It's one of the case study in AS shape of molecule. Ammonium ion, on the other hand, is to do with additive covalent bond using the lone pair on the nitrogen to take up a H plus. In doing so, you actually transfer the plus charge onto the nitrogen, so that's why it's a NH4 plus, and now you have got 1, 2, 3, 4. You got 4 sigma bond, 4 sigma bond meaning 4 bond pair of electrons, and you got 0 lone pair because you already used the 1 lone pair for forming the additive covalent bond. 4 bond pair, 0 lone pair, the 4 bond pair repel equally. You get tetrahedral geometry, which is 109 degree, whereas previously you have 107 degree for the trigonal pyramidal NH3 molecule. So in terms of option A, okay, so ammonia is a polar molecule. As you know, ammonia forms hydrogen bond because nitrogen is among the 3 most electronegative elements: oxygen, nitrogen, and fluorine, and is bonded to hydrogen. So obviously you can form hydrogen bonds between themselves as a result of it being a very polar molecule. Ammonium ion is non-polar, but of course it's ion, so we don't need to talk about polar or non-polar. It is a full charge, so there's no doubt about it. It is a cation. Alright, so we don't talk about dipoles, but if you can imagine anything in the tetrahedral geometry with 4 groups that are the same, the dipoles will cancel out, but here you have a full charge anyway, so it doesn't really matter. Of course, we already can see that option A is definitely wrong because this is a polar molecule. So option A is wrong because of that. Option B, it talks about the bond angle changes from 109 degree, but it changes from 107 degree to 109 degrees, so it increases, it doesn't decrease. Option B is wrong. This reaction is a redox reaction, it says. It is again wrong. This is acting as a base because it is accepting a H plus. This is acid, it is donating the H plus. And once the base accept the H plus, then you get this NH4 plus. This is called the conjugate acid, whereas the OH minus is called the conjugate base because it's the species that you get. Conjugate base is what you get after the acid donates the proton, and that will give you the conjugate base OH minus there. Alright, so all these terms, acid base, conjugate base, is stated in the syllabus under AS, acid and base chemistry. So these are not redox chemistry, these are in fact acid base reaction. So the water is acting as an acid donating protons. This is definitely option D as the answer there. Oops, I probably have enough space there. So yeah, question 16. What do they want? They're talking about similar ionic radii. So similar ionic radii. This is between Mg2 plus as well as RLi plus. Therefore, the corresponding compounds, their chemistry is similar. So similar reactions, similar chemical reactivity. So what can I say? Lithium burns very slowly in oxygen. So statement A is wrong because magnesium burns in oxygen with a very quite rapidly, and it burns with this very distinctive bright white light. If you've never seen it, it's kind of blinding. It's really bright. Okay, so we know A is wrong because following the chemistry of magnesium, it will definitely burn in oxygen similarly, I guess, very rapidly. In terms of B, what do I know about B? Lithium carbonate decomposes, forming lithium oxide. So we know that magnesium carbonate does decompose as part of group 2 carbonate to give you magnesium oxide and CO2. This is also quite a popular question to ask in practical, okay, as part of your AS paper 3 practical. And if magnesium carbonate can do that, you can imagine lithium carbonate can also do that to form Li2O plus CO2. So B is quite correct in terms of thermal decomposition. In terms of C, I'll just very quickly show why it is wrong. We know that MgNO3 twice will decompose, the nitrate will decompose to give you magnesium oxide and NO2, so 2 of that NO2, and you get O2, which is half of 2, so you get brown gas NO2, and you get this colorless gas oxygen, which you don't usually see. Of course, you don't see colorless gas, but when you get this brown gas, usually you would test for this oxygen because you know it goes together with the decomposition of group 2 nitrate, group 2 nitrate, okay, which means, you know, They say lithium nitrite, LiNO2. So you get an oxide, you don't get a nitrite, which means, you know, option C is actually wrong if you want to say it follows the chemistry of group 2 carbonate. All right. Last but not least, we know D is obviously wrong because we got the answer as B already. It says lithium violently with cold water. Violently with cold water, and that is not true because we know that magnesium doesn't react with cold water. Magnesium has no reaction with cold water. In fact, the only way you can react magnesium with H2O is Mg plus H2O steam. This is steam, so there is no water at all. So you will not get magnesium hydroxide. Instead, you get magnesium oxide and you get hydrogen gas. This is a distinctive reaction from your O-level or IGCSE chemistry. This is done at very high temperature. Magnesium does not react with cold water at all. Lithium, therefore, will not react with cold water if it follows the chemistry of magnesium. So option D is obviously wrong there. Question 17. Which statement about group 17 elements and their compound correct? So you're looking at a correct statement, so group 17 chemistry. If we look at option A, it says chlorine with NaOH, but they say coal. When it is coal, it does not go to the higher oxidation state. It just stops at chlorine -1 and also chlorine +1. This is going to be chlorate 1 is NaClO because ClO minus ion together with Na plus. This is a -1 oxidation state overall. Chlorine is the unknown and you got 1 oxygen. So each chlorine is going to be -1 +2. Chlorine there is going to be +1 there. Okay. Anyway, nope, I don't want that. What do I want? Okay. So there will be plus H2O there. So you got to be able to balance this. This is one of the easier one to balance. And then, yep, this one is balanced then. Okay, so you do not get NaClO3 because in this disproportionation, this is a mild disproportionation. This reaction is called disproportionation. In one of the earlier question, I talked about disproportionation earlier, where you have one species getting both oxidized. Chlorine 0 to chlorine +1 is actually your oxidation and is also reduced in the same reaction. So this is called disproportionation, mild because you are at a fairly mild condition, cold temperature. Now the next thing is about thermal stability. So we know in terms of thermal stability, we are breaking. We need to break covalent bond. We need to break covalent bond. So HX will break into H2 plus X2, where X is halogen. And then the reason they give is about electronegativity. So it's the wrong reason. It is not to do with electronegativity. It's to do with bond strength. It's to do with the covalent bond strength that you can get from the data booklet. But you also know the halogen atom gets bigger down group 7. So this bond gets longer. Longer covalent bond actually means weaker covalent bond. Therefore, it becomes easier to decompose or to just break it down by heat. So HBr is actually less thermally stable, but that is for the wrong reason. So that's why it's actually wrong. The trend they give is actually correct, but the reason is wrong. If you look at option C, they say iodide ions are oxidized to iodine by corn sulfuric acid. This is my most favorite kind of line diagram. I like to talk about these in terms of group 7 chemistry. Group 17, well, in the context of A-level chemistry, this is oxidizing power. We talk about chlorine, bromine and iodine. We don't talk about fluorine that much, at least for the Cambridge curriculum, but fluorine will be a stronger oxidizing agent than chlorine, than bromine, than iodine. So corn sulfuric acid lies somewhere in between that of chlorine and bromine. It has to be concentrated for it to be oxidizing agent, and it is a stronger oxidizing agent than I2. Therefore, it can oxidize I- to I2. All right, this is one of the classic X- corn sulfuric acid reaction. AS syllabus, which of course they can and they will ask you in A2 paper 4 if they want to. All right, in part D, we know C is the answer, D must be wrong. They talk about soluble and that is actually wrong. it's supposed to be AgCl, solid, that is soluble in excess aqueous ammonia as part of your practical. And I talked about this earlier. This is a white precipitate. It will give you this complex with 2 ammonia. Complex ion is part of A2 transition metal chemistry, but you will have seen this as part of your AS organic chemistry, because this is Tollens reagent. So you have Tollens, which is a source of silver 1, which is soluble and is colorless, and when you react with aldehyde, it will reduce it will oxidize aldehyde to the carboxylate, and of course on its own it will get reduced because it's acting as oxidizing agent, and you go for silver +1 to become silver 0, which is the silver mirror. Okay, so silver chloride is soluble, but silver iodide is insoluble. Okay, silver iodide is insoluble in aqueous ammonia, not even in concentrated ammonia, so therefore we are left with option C as the only correct answer there. Question 18. So this is ammonium salt. I just like to give you the idea of this thing where you have what am I talking about here? H plus OH minus give you H2O. This is your classic neutralization. This accepts H plus, the acid of course donates H plus. Now what do we have here? The classic condition would be any hydroxide react with NH4 plus, it will take away, it will accept the H plus, and then you will get H2O, and then when this one loses the H plus, it donates the H plus, then you will get NH3. This is your classic ammonia displacement when you react ammonium salt with any hydroxide, any alkali. Now you have quite a lot of option here. This is your ammonium chloride, so you look for hydroxide. Look for anything that looks like this, anything that looks like hydroxide, because obviously this question doesn't have hydroxide given in front of you. Option A is wrong because it's a carboxylic acid. So carboxylic acid is the furthest thing from hydroxide, it's the total opposite, so you don't go for carboxylic acid at all. If you look at option B is ethanol. It's ethanol, so it's an alcohol. And if it is alcohol, it is not like a hydroxide because one thing, it doesn't have a charge, and you have a better choice, which is option D. Of course, I'll just go through option C first, which is an ester. So you have CH3, CO2, CH3. No, that's wrong. Should be CH3, CO2 like this, whereas these two things are molecule, no charge on oxygen. Okay, so not like hydroxide. And option D definitely works because what you have is what you call sodium ethoxide. Not too sure if you know the name. When you have alcohol reacting with sodium, then you get this thing, CH3, CH2O minus. They don't show it as O minus, but hopefully you can see that it's actually O minus and a plus. It's a giant ionic structure because it's an ionic compound, something you have known from O-level, something you have known from O-level or IGCSE chemistry. And think about how you produce it is actually part of AS alcohol chemistry, because when you react alcohol plus sodium, you're going to get alkoxide. Okay, and you will get half H2. This is a gas, this is aqueous, because, well, not aqueous, sorry, because the ethanol itself is in ethanol, so this is in ethanol. Okay, yeah, I mean, this is what you classify as a redox reaction, which a lot of people are confused about, because so this is sodium 0 and you have Na plus because it's a salt. So very clearly there, D is the correct option, having ruled out the other three choices there. Moving to the next question, so question 19. So we have X. X is an oxide of period 3. So as you know, period 3 oxide is part of your AS inorganic chemistry case study. And then when you add it in water you're going to get acidic solution, meaning the pH is going to be lesser than 7. The fact that it dissolves in water and it is an acidic oxide, so you can imagine it being an acidic oxide. So it's going to be the non-metal oxide on the far right of the periodic table, because on the far left, sodium oxide and magnesium oxide is going to be sodium magnesium oxide is going to be basic oxide. So we know Na2O, MgO is what you call basic oxide, because they dissolve in water to give you the sodium hydroxide and magnesium hydroxide respectively. On the other hand, we know the Al2O3 as well as SiO2, they are insoluble in water, so they will not react with water, they don't get hydrolyzed or whatnot in water, and therefore they remain as pH 7 for their water. Having said that, that means I can rule out option A, which is Al2O3, and option B, which is MgO. Then I'm left with between options C and D, both of which are oxides of non-metal, phosphorus P4O10 as well as SO3. Both of them will give me acid in solution. That is where the calculations bit of the questions are important. If we look at the mole of the NaOH required, the information of which is 25.0 cm cube, convert to dm cube, multiplied by the concentration in mole per dm cube, pop that into your calculator, and you get 2.5 times 10 to the minus 3 mole. What else do we know? Let's see. If we have option C, then we know that P4O10 plus H2O, this is phosphorus plus 5. I know the acid I get will be phosphorus plus 5 because it has the PO4 3 minus ion. So the acid I'll get is H3PO4. This is because it's not a redox reaction, it's just the P4O10 getting hydrolyzed in water. And of course, every equation you write has to be balanced. There are 4 phosphorus, so there are 4 phosphorus, and now there are 12 hydrogen, so there are 6 times 2, which is 12 hydrogen, 6 oxygen plus 10 oxygen, so 16 oxygen there. So having done that, I know it's H3PO4. H3PO4 has 3 H plus, so you know when you react with NaOH, you need 3 of the NaOH to react with 3 of the H plus, so you're gonna get 3 H2O, and of course you're going to get Na3PO4. The most important thing really is the mole ratio, 1 mole of acid with 3 mole of the hydroxide, because 1 mole of the acid has 3 H plus, 3 times H plus per acid. So in terms of my calculation, I can be thinking about the mole of H3PO4 is to the mole of NaOH is 1 mole of H3PO4 will react with 3 mole of NaOH. And what can we say here? If that is true, then they say compound X refers to this. If I say if this is X, then this giving you this, giving this reaction. What can we say here? Let's see. So between C and D, right? If I work out C is the answer, then C is the answer. But you know, if I work out that C is not the answer, that means D must be the answer. All right, so that's the way to save time in MCQ. P4O10 to H3PO4. So P4O10, 1 mole of this give you 4 mole of H3PO4. Yeah, from the second equation, 1 mole of H3PO4 reacts with 3 mole of NaOH. So reacts with NaOH. 1 mole of H3PO4 reacts with 3 mole of NaOH. This is not the same, this is not 4, so what I can do is I can multiply this by 4, and whatever I do on that side, I have to do on this side, so that becomes 12, and hopefully you can see now 1 is to 4 is to 12. Now because both of these become the same number, so I can, you know, compare the same mole ratio. This is actually a shortcut to this calculation. And having done that, what I could do next is I need a bit more space. So this is my part 3. What else can I do? The mole of P4O10, which is X, is to the mole of NaOH, which, you know, I have the mole of NaOH that actually reacts. From the balance equation, from the balance ratio, 1 is to 12, because 1 mole of P4O10 reacts to 12 mole of NaOH. Now what is my job here? I know I reacted 0.100 gram, so 0.100 gram divided by the MR of which P4O10 is actually 284. And then what else can I do? I can find the mole, the actual mole of NaOH that reacted. So make that the subject. So the actual mole of NaOH will go up there. And then you get 0.100 over 284. And you need to multiply that by 12. So that multiplied by 12. And I get 4.23 times 10 to the minus 3 mole. So it means if you have 0.100 gram of this X in this mole ratio, you will need 4.23 times 10 to the minus 3 mole of NaOH. But this is the actual mole of NaOH that actually reacted with the acid produced from the oxide of the nonmetal. So having said that, you can see that these and these are not equal. So this is not 2.5 times 10 to the minus 3. Therefore, oops, I don't want that. Therefore, not C. Answer is D, because I've just hopefully convinced you that C was wrong based on the amount of NaOH that is actually required not being equal, and without having to do the last one because I've done everything correctly for my option C there for my calculations. That means D must be the correct answer if C is incorrect. On to the next question. So question 20, this is about they give you CH2, CH. There's so many CH, all right? What I'll tell you is draw skeletal, all right? So this is a CH2 terminal, and this is a CH, and then like that, and then like that, and then like that. Altogether, you have 1, 2, 3, 4, 1, 2, 3, 4. You have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We draw zigzag in order to show the geometry like this. Of course, it could be cis, it could also be trans, but we need to be careful because this is a terminal CH2, meaning to say there are two groups, there are 2 times same hydrogen atoms on the same carbon, on the same carbon of carbon-carbon double bond. So the same thing goes for this as well. So meaning to say you cannot have cis and trans there. So you can only have cis and trans here, here, and well, that's all really. So you can't have cis and trans there. You can't have cis and trans there because there's terminal CH2 for this other second criteria for cis and trans isomerism. So what you can have then therefore is just between these and these. And these are one of the most confusing questions of all, because then you can draw and imagine that you cannot have cis and trans there. So this is going to be trans and trans, T and T. So if I have trans there, and then I have cis there, so trans and cis because these two are on the same side. And then how about if I actually draw cis, meaning these on the same side, and then I'll draw trans on the other side. So this is cis and this is trans. Am I correct? No, I'm not correct. I'm missing a double bond at the end. I'm missing a double bond at the end. I'm missing a double bond at the end. So this is still the cis for that second carbon-carbon double bond and trans for the third one. And then the fourth one, as you can imagine, will be the trans and sorry, cis and cis. So cis and cis. So cis and cis. And remember, you can't have cis and trans at this terminal CH2. But then obviously, I hope you can see then that this is one isomer. These two are the same because of the symmetrical structure. So a lot of students, they will have thought that, okay, they've gotten to this stage where they have found two centers that can form cis and trans, but they forgot that the idea is the left and the right hand side are totally the same because it's a symmetrical structure. And having said that, the trans cis as well as the cis trans are exactly the same. Okay, so you can convince yourself by rotating the structure and you will see that they are exactly the same. Okay, if you rotate this by 180 degrees like this in the plane, you will get exactly this one, which means there are only 3 isomers. All right, so there will be option B and not 4 isomers as you would expect from 2 square. So be very careful about symmetry there. Next one, question 21. So you are asked to name this compound. So in terms of naming compounds, you want the longest chain carbon. So if I name this as 1, 2, 3, 4, 5, because this is the longest chain carbon compared to that. Of course, then you can also have 1, 2, 3, 4, 5. your most important group here will be alcohol, more important than alkanes. Therefore, you want the lowest number for the important one. So number 4 is bigger than number 2, so I can cross out the one in pink. So we are looking at something 2-ol. So it's something 2-ol versus 2-hydroxy. So which one is more important? This one is more important. So alcohol more important than alkane. So we will end up with 2-ol, which means we're left with B or C. A can cross out, D can cross out. Between B and C, then you need to look at where is your alkyl chain. Is at position 3. There are 2 of them. So this thing is called 3,3-dimethyl. So overall, your compound name will be 3,3-dimethyl. Pentane 2-ol, because there are 5 carbon in the longest chain. OH is at position 2, so it's 2-ol. You've got 2 methyl groups at position 3,3. So obviously this is 3,3-dimethyl. Pentane 2-ol, which is option C there. Question 22 is about the repeat union of this polymer. So what do we have here? We have CH2, CHCl, and then CH2, CH double bond, CH2. So they're telling us that is the repeat unit. So there's the information there, repeat unit, so they get repeated. And they say there are 2 different monomers. So the fact that these are polymerization in AS, and you know condensation polymerization from your O level, and you don't see any polyester, in fact you don't see any ester, you don't see any amides, they are from your O level, IGCSE chemistry, because these are addition polymer. When we talk about addition polymer, we are thinking about carbon-carbon double bond, or in fact carbon-carbon triple bond, which is less common in your A-level chemistry. I hope you can see that this is actually one repeat unit. And that will be the easier one, which is CH, H double bond, CHCl. This is your vinyl chloride, or you just call it chloroethene. So you can also call it chloroethene. It's the monomer to make polyvinyl chloride, which is PVC. And the other one, if you could see what is happening there, is this thing here. Quite funnily, you have a carbon-carbon double bond there, but this is the result of the actual carbon-carbon double bond being here as well as here. This is a strange one, as I'll prove it to you. So CH2, CH, and then CH, CH2. So if I draw the skeletal formula, you will see a CH2, and then CH, because carbon form 4 bond, 1, 2, 3, and then H, and then single bond to the CH, single bond to the CH, and then double bond like that. Well, 1, 2, 3, 4, 5. I think I've gotten extra carbon. That is wrong. Let me see what is wrong. So I've gotten 4 carbons, CH2, CH, CH, CH2. Okay, so there's a single bond there, and in fact it's probably better if I draw the display formula, then it will become clearer. So H, and then C, and then H, and then C, H, and H. Each of these carbon is trigonoplanar, 120 degree, sp2 hybridization. Okay, so each of them are trigonoplanar, carbon sp2. This molecule is totally planar because there's no other tetrahedral carbon or any other hybridization apart from sp2 carbon there. Okay, so looking through the options, they look very tricky, but hopefully you can pick up that these and these are the option number B. So the rest of the option will be wrong for various reasons that it will become clear if you look through the monomer. And you could think about the mechanism being, in such a way that something will attack there, and then this is carbon-carbon double bond, it will attack there, this will go there, and then this will attack another one of these alkene, such that you're adding onto double bond, and this thing will alternate the double bond like this. From the end, move the double bond to the center between 2 and 3. That is why in your polymer, you get the double bond between the 2 and 3 carbon 2 and carbon 3, and then you add via the terminal carbon again. So that's option B there. Question 23. What do we have here? We have CH3, C and then CHO. So this thing there is aldehyde, and the carbonyl on the other side, this is a ketone because it's a carbonyl bonded to carbon and carbon, whereas this is a carbonyl, because if I draw the carbonyl out, it will look like this. So there's the aldehyde there. So the carbonyl is bonded to carbon and hydrogen. This is the RCHO. This is the aldehyde group. Now, if we look at the reactions, they say the ketone and the aldehyde, right? So if I just look at ketone as well as the aldehyde group, if we look at option A said this is acidified potassium dichromate 6. So this is chromium plus 6. I'll leave it as an exercise for you to work out the oxidation number there. But this one is oxidizing agent. It's orange in color. And ketone is not oxidized further, but aldehyde can be further oxidized to give you carboxylic acid, and you will see orange to green coloration there. This question asks for react with only one of the two functional groups. We already gotten our answer, but let me just go through very quickly in terms of what kind of reactivity would the other reagent undergo. Okay, 2,4-DNPH refer to when you have 1, 2, so it's NO2 there, 3 and then 4, so you have another NO2. You have a 2,4-dinitro phenyl hydrazine. So this is a hydrazine, NH and NH2, and then bonded to another one. 2,4-dinitro phenyl hydrazine. Okay, phenyl refers to this benzene ring there. And they will react with ketone and aldehyde. You will get an orange PPT. So observations are very popular in structure paper as well as in theory papers, of course. Okay, so orange to green with the oxidizing agent dichromate 6 acidified. Orange PPT for both of these ketones and aldehydes carbonyl. On to the next one, you have Hcn Hydrogen Cyanide. Don't forget you need NaCN catalyst to kickstart the reaction, and you also need it to be cold around 0 to 10 degrees Celsius. So Hcn, this is a nucleophilic addition reaction, and you can do that on the ketone as well as the aldehyde, so that can't be the answer there. And finally, NaBH4, this is a reducing agent, and you can reduce ketones to secondary alcohol, and you can reduce aldehyde to primary alcohol. All right, so aldehyde get reduced all the way to primary alcohol, ketone get reduced all the way to secondary alcohol. Already got our answer A, we couldn't move on at that stage. 24, so question 24, ethanol can be converted to ethene. So if I just draw ethanol converted to ethene in a single reaction, you have to kick out H2O, because when you add H and OH, which is steam, across alkene, you get alcohol. That one is all level at IGCSE chemistry. Then this is just the opposite of the addition. What you're doing is called elimination. This is the type of reaction stated in AS organic chemistry under introductory organic chemistry. Of course, you know the specific name is dehydration. And then the other one is ethanol can be converted to bromoethane, and then you can, if you use you don't use NABR, what do you use? You use HBr as a gas, hydrogen bromide gas, or you can use phosphorus and Br2, and then you will kick out other product as well. So this is going to be let me try and change the color of that, because it will look a bit better. And then this reaction there is called nucleophilic substitution. So this one you need a catalyst. So typically we will use SiO2 or alumina, so Al2O3 catalyst. So you heat a cotton wool soaked with the alcohol and pass it over this catalyst bedrock, and you collect this as a gas, which is insoluble in water, so you can collect via downward displacement over a water trough. This is a reaction that doesn't require a catalyst, so it happens under reflux in this with this particular reagent, so you don't need a catalyst for this, which means our answer there must be option B. Pretty straightforward there. Question 25, so we have diols. Diols mean two hydroxy groups bonded to the same carbon, OH on the same carbon. it can minus water, so they can spontaneously eliminate a molecule, so -1 water, and give you a carbonyl. So you are looking for, after complete hydrolysis, you want to get silver mirror with tolerance reagent. So we know tolerance reagent consists of silver 1 complex. So tolerance reagent is actually silver diamine, so with 2 ammonia, and this is a plus. This is a colorless solution. So what happened is, this is a test for aldehyde. Aldehyde would actually turn to form this silver mirror. So this is a test for aldehyde, and it will not work for any other alcohols or whatever, only for aldehyde. Let's see, so we need the idea is we are looking for aldehyde, and we are looking at let's see. Okay, I think I see it now. Okay, so they say after complete hydrolysis, if you look at the options given, these are all halogenal alkanes. Halogenal alkane undergo hydrolysis and they give you ROH, and there is the beginning of this particular information where you have 2 OH on the same carbon, and you kick out the H2O and you get a carbonyl, and this carbonyl compound can be ketones or aldehydes, but you want something that will give you a silver mirror with tolerance, so you want something that will remove the water and give you an aldehyde. So first of all, complete hydrolysis, to give you the ROH, you need the 2 OH on the same carbon. That is a very, very important information. 2 OH on the same carbon mean that we can have option A or option D, where it's 1,1 or 2,2 dibromo. Option B and option C, you can cross them out because the halogenal alkanes are not on the same carbon. If they are not on the same carbon, then you're not going to get 2 times OH on the same carbon. You're not going to get this particular thing happening. So let's have a look at option A. With option A, we have 1,1 dibromo, 1, 2, 3, 4. So we have Br there and Br there. If we do hydrolysis, so that means they become OH. That become OH, 1, 2, 3, 4. Oops, sorry, I was wrong. No, it's 1,1 dibromo, 1,1 dibromo. So it's 1 there, and it's 1,1 dibromo, so that's going to become OH there. Okay, and I can remove that. Oops, that's not what I want. 1, 2, 3, 4. OH, OH, so 1, 2, 3, 4. Remember that we could kick out 1 molecule of water. That's what the information told us, and we'll get a carbonyl. So if I just kick out 1 molecule of water, doesn't matter where it is, as long as I kick out water, then I'll get, oops, there you go, 1, 2, 3, 4. So this is a terminal, the terminal carbon there, and because it's a terminal carbon, when you remove H2O, you're going to get an aldehyde, and remember that your aldehyde is the one that will turn the tolerance reagent, which is this thing, into silver mirror, because your aldehyde get oxidized, and this thing is the oxidizing agent that gets reduced to give you a silver mirror with this particular tolerance reagent. So A is the answer we're looking for. If you go for D, then you will have 2,2 dibromo, 1, 2, 3, 4. Unfortunately, there is extra carbon there. So 1, 2, 3, 4. So this thing will not give you aldehyde. In fact, it will give you ketone. I'll just show you very quickly. So like that, and then you can kick out the water, and then you will get ketone. I have drawn it slightly differently. Let me just draw it so that it's a bit clearer. Like this is a ketone. Ketone does not give you a silver mirror with a tolerance reagent, so that's why option D is incorrect there. Question 26, what we have here is which alcohol will give a yellow precipitate with alkaline aqueous iodine. You're in alkaline condition, aqueous iodine, this is the iodoform test. And in the syllabus, the iodoform test is broken down into 2 things, which is in the alcohol topic, CH3CHOH, as well as in the carbonyl compounds topic, which is a CH3CO test. This is your methyl ketone, so it's a very classic, a very, very old test. This is a methyl ketone test. and in both of these cases you will just kick out one of the CH3 there, and you also kick out one of the CH3, then you will get CHI3, you get CHI3, and this particular thing will become carboxylate. They are carboxylate anion because you are in an alkaline condition, so you will not get carboxylic acid unless you protonate it at the very end there. So this thing there will become carboxylate anion as well. So carboxylate is an anion, so there's no point of me saying it any further, but you lose one carbon, and it is this thing that is the yellow precipitate, triiodormethane. Triiodormethane has another name, it is called iodoform. Alright, so based on A, B, C, and D, if you look at A, I'm just going to draw skeletal because that's my favorite thing to draw. And you're supposed to be getting better at skeletal as you progress through the course, because there's no way of doing A2 unless you are very good at drawing skeletal. It's the fastest, it's the most elegant. You got to be able to do it because questions will give you skeletal formula. CH3 twice, CH because carbon from 4 bond, 1, 2, 3, so there's a hydrogen. CH3CH, carbon from 4 bonds, so there's 2 hydrogen, and then there's OH. So there's nothing that resembles CH3CHOH or CH3CO. A cannot be the answer there. B there, this is a tertiary alcohol because the carbon with the OH is bonded to 1, 2, and 3 carbon, whereas previously this is a primary alcohol because the carbon with the OH is bonded to 1 other carbon. Anyway, that's not the essence of this question. You don't have a CH3CHOH, so B is also out. C, what do we have? C here. We also have a tertiary alcohol. So again, there's no CH3CHOH here because there's a carbon with 4 bonds. So that means there's no hydrogen there, which means option D must be what we want, which is correct because option D is CH3CHOH. In fact, you can see it from the question itself. So they tell you it's a CH3CHOH. So straight from the syllabus, they are not even lying to you at all. CH3CHOH, they will give you the test for iodoform, a positive test with iodoform with alkaline aqueous iodine to give you the yellow precipitate, which is the iodoform being formed straight on the alcohol syllabus of the curriculum. Question 27. So what do we have? Structural isomers. You want a red PPT. You want it with phalanx. So phalanx solution is a blue color solution. It's a pale blue solution. That is because it's a complex containing copper 2 plus. So copper 2 plus with some other stuff around it. But essentially it's a pale blue solution. Then they will go to Cu2O, which is copper 1 oxide, and that is your brick red PPT. If aldehyde is present, if RCHO is present. So realistically speaking, we are looking for aldehyde. So we are looking for aldehyde because we want to turn phalanx reagent brick red. So look for aldehyde, look for 5 carbon aldehyde. And they are looking for structural isomer. So we are not looking for stereo at all. So even if you have a pair of stereo isomers, you're not going to include them because you just want the structural isomers. Couple of things they want. Look for aldehyde with 5 carbon, look for structural isomers only. So let's get started with drawing. So I'm just going to draw 5 carbon. So 1, 2, 3, 4, 5. And then I'll draw the aldehyde. So this is the CH double bond O, so CHO 1, 2, 3, 4, 5. This is called pentanal. This is a 5 carbon aldehyde, and there's no chiral center or whatever because well, there's no chiral center to begin with, but we're not looking for any of those stereoisomers because we just want the structural isomer. So after the straight chain, I'll be looking for the branch chain. So the chain isomer. So this is 1, 2, 3, 4. Where can I put the 1 extra carbon? I could start by putting it at position 2. I cannot put at position 1 because it will be a ketone otherwise. Alright. So there is a chiral center here, but then we are not counting the stereoisomers because there will be not structural isomers. Be very careful, yeah? So again, I have the 4 carbon straight chain, but then I have 1 other carbon, so I can put at position 3. I can put at position 4 because they will just extend it to 5 carbon straight chain. So there is no chiral center here because these 2 groups are the same. There's another hydrogen there, by the way. I've got the 3 so far. Is there another one? Let me see. So there's the one with 4 carbon. I wonder if I have 3 carbons. So 1, 2, 3. So where can I put my 2 carbon? I can put it there, but there will be that. I can put it there and there. If I put it here and here, this will become 1, 2, 3, 4 because that's the longest chain carbon, and this is exactly the same as this because the methyl group will be a position 2, branch at position 2, so I don't want that at all. What I can do, however, is 1 carbon and 1 carbon, so I'll have 1, 2, 3, 4, 5. So this is called 2,2-dimethyl. And then the most important carbons are, well, the 3 carbon aldehyde, so it's called propanol. So 2,2-dimethyl propanol. There's no chiral center there. Altogether there are 4 of these structural isomer. Even though there is 1 chiral center, we don't count the stereo isomer because specifically they ask for how many structural isomer. We're looking at option D there. Question 28. So which statement about the use of alkane fuel is correct? Reacts with oxygen and nitrogen. So if we look at option A, we can think about C8H18 undergoes combustion. So combustion is in oxygen and you will get CO2 and H2O provided you get complete combustion. And then they say it reacts with nitrogen in the air. In nitrogen, no reaction, but the high temperature can cause the nitrogen in the air to combine with oxygen in the air to give you the oxides of nitrogen as a result of the very high temperature generated from the heat due to the combustion, which is always exothermic to begin with. Okay, be very careful about the statement. A is definitely wrong. And then they say in limited oxygen. Limited means not enough, or what we say insufficient. So we are going to get incomplete combustion. And when you get incomplete combustion, you are going to get carbon monoxide. But carbon monoxide has a toxic effect on hemoglobin. It doesn't oxidize the SO2 to SO3. For that, you need the NO. Okay, so SO2 to SO3. This one need the NO2 in order to do that. Okay, so the NO2 will lose the, let me just write the equation, SO2 plus NO2. The NO2 will lose the oxygen, it will oxidize SO2 to SO3, and itself get reduced like this. This is the correct equation. It doesn't involve CO, it involves NO2 instead. So option B is also wrong there. Option C, catalytic converter. So your catalytic converter basically converts dirty or harmful gases into cleaner gases. So harmful gases, before they leave the car exhaust, they will become cleaner gases that are not so bad as pollutants. They say involve removing NO2, which is correct, because what happened with the NO2? Let me think. Does it remove NO2? I know it remove NO. So what happened with NO is they will react with CO to give you N2, half of that, plus CO2. So that happens. And then they say remove CO2, which is definitely wrong, because, well, if you have incomplete combustion, if you have unburned CXHY, then what happened is you will burn them completely to give you CO2. So this equation is not balanced, by the way. I am well aware of it. So this is actually what happens. So, you know, this equation is not balanced, so don't quote me on this. However, so what I can tell you is that CO2 is a byproduct of unburned hydrocarbon that the catalytic converter will be involved in. Alright, so C is definitely not what we're looking for. If A, B, and C is not what we are looking for, that means D must be what we are looking for. D is the correct answer. So as I said, unburned hydrocarbons, you do react them, and NO2 is also produced due to the high temperature from the car engine that allows the nitrogen and oxygen to react to give you NO, and the NO can go on to form NO2. So this photochemical smoke is a real problem. It's not SMOKE, this is a SMOG. This is a real problem. It causes respiratory distress, meaning to say, in simple terms, they call it respiratory distress. You could call it really serious breathing problems. This is a huge issue in some countries that have a lot of factories that uses a lot of petroleum, and they also produce quite a lot of NO2 gas as a result of a large number of vehicles actually. So question 29, this is a big compound. This is compound Z. If I just draw Z first of all, so it's got a cyclohexane 6-member ring, and it's got an ester as well. So I hope you can see the ester already. It's got alkene. It's got quite a number of hydroxyl alcohol. So this is Z. Let me just label what is what. This is carboxylic acid, so something you know from your O-level or IGCSE there. That is alkene, carbon-carbon double bond. This is ester. These things are alcohol, so alcohol, as well as alcohol. Now, what do they want? They want sodium carbonate. So sodium carbonate reacts with acid. So you're looking for just the carboxylic acid group, reacts with carboxylic acid. What is produced in a good yield? So normal alcohol only produces H2 with sodium metal in a redox reaction that I talked about in one of the earlier questions. So this is an acid plus carbonate reaction, so it's just this particular thing that will react. So I can probably just copy down the whole thing, and then I can just paste the whole thing. I just need to remove a couple of things there. Remove that, remove the H. So the ester doesn't react with sodium carbonate, not the alkene, not the alcohol, but the CO2 minus, the CO2H becomes COO minus like this, and they become a plus like that. And of course you will get CO2 plus H2O as well, because it's a acid plus carbonate give you metal salt, plus CO2 plus H2O. So this answer here is option A. I always like to draw my ionic structure with an O minus Na plus, because some students would draw as a covalent bond, which is very clearly wrong. And as shown on part A or option A, they never really show the charges, because they expect the student to actually know that these are giant ionic structure. These are now ionic compound. On to the last question. This is question 30 in this section A of this MCQ. This is to do with infrared. So with infrared, this is compound G. So what can we see in this infrared compound G? Number one, there is no broad strong adsorption. So this broad strong adsorption is very characteristic of OH, and this is around 3000 to 3500 wave number, give or take. So the fact that it's absent means no OH. Oops, what am I doing? No OH. How about number two? We're looking for carbonyl. So there is a strong, sharp absorption at around, if you have a look at around 1750 wave number. These are the units as shown on the graph, on the table, sorry, not the table, not the graph, the diagram itself, the infrared spectrum, and this indicates that you have C double bond O. If we look at further down, so this one is not so obvious, but then it will be obvious once you go through the options. Perhaps I'll go through this number 3 in a little bit after I actually use number 1 and number 2 first. So if you look at option A is out because you have CH3CO CH2OH, you have OH, so A is out. And you can cross out B because B is a carboxylic acid. B also has OH. This is a carboxylic acid that is COOH, so B is out because we just said no OH. So between C and D, how do I decide between C and D? Well, the answer is obviously C, because this one has no OH but has C double bond O, whereas if you look at D, there is no C double bond O at all, but of course we have this C double bond O, which is around 1750 wave number. Very strong, very sharp absorption that hopefully you can see it and you will be able to tell. Okay, this option number 3 is not so obvious, because just from working out that C is the correct answer and not D, from option C you can check CH3, COO, CH3. We have these, which we already checked, but we can also check for this one, CO of an ester. If you look from the data booklet as well as from the infrared spectrum itself, you will see that this is a sharp, well, reasonably sharp, strong absorption for the CO stretch of an ester at around 1200 wave number there. Okay, although these are the two most obvious ones, obviously once we identify as the ester, which is from option C, we can also see this as well, which we know of course makes sense based on the structure given. All right, so that's the end of that section A, 30 questions on that MCQ. Onto the section B of this paper. So section B is a bit of logical thinking. We always check statement number 2 first. So in this question 31, we have phosphorus, well, we have a phosphide ion versus 37, 19, and K plus. So this is about counting the number of protons, electrons, as well as neutrons. So let's get started. The number at the bottom there tells you the number of proton number. This is the number of nucleons, which is the total number of protons and neutrons. These are charges. This has gained 3 electrons from the atom, and this has lost 1 electron from the atom. So there's 15 proton and there's 19 proton, and these are ions. So this one has gained 3 electrons, so it's 18 electron. This one has lost 1 electron, so it's 18 electrons. In terms of the neutron, 13 minus 15 give you 18. And 37 minus 19, that give you 18 as well. They say common. They say which one is common between the two. Well, this one is common, this one is common, this one is not common. So electrons is option A. Oops, sorry. I should really have been more careful about this. Electron is option 1, neutron is option 2, protons is option 3. So this is option 1, option 2, option 3. So, 1 and 2 are correct. So that means option B there. Okay, so B is the correct answer. Question 32, the repeat unit of a polymer. So you have this polymer, which is CH, HCN, as well as CO2, C2H5. Looks complicated, but let's see what is going on. So this is a nitrile functional group. This is C triple bond N is what you call a nitrile. This thing is an ester, whereas this thing is an alkyl, basically just alkane really, C2H5. You want in the solid polymer, so it's a long chain. So in the solid polymer, you want the intermolecular forces in between the molecules. What kind of forces of attractions are there? Let's see, if you have RCN, you will have delta minus and delta plus there. When you have ester, you will have things like this. Of course, the R are not necessarily the same. I'm just making my point here that this is delta minus, and delta plus. So we're talking about dipoles here. So there is permanent dipoles, but there is no hydrogen bond because no hydrogen bonded to O. Remember that in an ester, the hydrogens are bonded to carbon, not the oxygen itself. So you don't have oxygen, you don't have hydrogen bond among the ester there or between any esters. You don't have any hydrogen bond there in nitriles because there's no hydrogen in CN as well. Yep. Okay. So no OH. What did I say? No OH. No hydrogen bond. Okay. I don't mean that. No H bond. Because no hydrogen bonded to O or N. Okay, so which means 3 is wrong. 3 is incorrect. How about number 2? Number 2 is about permanent dipole. I just shown you that they are permanent dipoles, and you can have interaction between this permanent dipole from one chain of the polymer to another chain of polymer, meaning intermolecular forces. Temporary dipole, option number 1 is van der Waals. So obviously you have electrons in the system. You can have 1 and 2. Is correct, well, are correct. So, that means option B there is the answer. Question 33. This is about Hess cycle. So, R to S, R to T. If I just draw the whole thing first, then this thing is plus 92 kilojoule per mole. And then this thing is minus 134 kilojoule per mole. And this is given as delta H equal to minus 75 kilojoule per mole. So Hess law says that the enthalpy change of a reaction does not depend on which path you take, as long as you start from the same reactant and end out the same product. So you could go this path or you could go this path, and then the enthalpy change should be the same. You're looking for which statements are correct. So which one are correct? Let me check number 2 first. If I check number 2, it says T to S is endo. Is that correct or not? Endothermic means delta H is greater than 0. So T to S. So which one do I have the value? I have these and these. So I could go this way. This is in the same direction, so minus 75. This is going the opposite direction, so it's minus bracket plus 92. So I would say the delta H there, delta H number 2, let's say, delta H number 2 is equal to minus 75 kilojoule per mole, because you're going the same direction. Going on the opposite direction, so it's minus bracket plus 92. I probably don't need to press my calculator at all, because minus and then minus times plus is minus. So I can show you the working. Minus 75 minus 92. I can tell you it's going to be negative, because minus and minus will give you negative. So this means this is going to be exothermic, which means, go back to this thing is wrong. So number 2 is wrong. So therefore, only one is correct, which is option D. And of course, you can check for that if you want to. All right. Question 34, you are looking for this definition of dynamic equilibrium. They're asking for which one is correct, but it's actually basically a question on definition of dynamic equilibrium. So if you look at option 2, no overall change, this is option 2, no overall change in the concentration of reactant and product, and that is correct, because no overall change means their concentrations remain unchanged or constant. So some students don't like this word constant. You can talk about unchanged or no overall change. It's the same idea. So they can be equal, they don't have to be, okay, but there's no overall change once you reach an equilibrium. How about number 1? Number 1 is definitely correct. It's to do with rate of forward reaction equal to the rate of backward reaction, or they call it reverse reaction at dynamic equilibrium. Okay, so you have a dynamic equilibrium there. Now there is no change in the measurable properties of a system. It's hard for me to actually justify this. Let me think of a way. Measurable properties of the system. I wonder how can I explain this. There's no change in the measurable properties of the system. Oh yeah, because it's at equilibrium. So at equilibrium, measurable properties. This is at a particular temperature, at a particular volume. At a particular temperature, volume, as well as pressure. At equilibrium, so meaning you can't change. Well, there's no change at all because it's at equilibrium already. Okay, so if 1, 2, and 3 are correct, so that means we are looking at option A as the only correct answer for question 34. Got me hesitating a little bit there. Question 35. This is about group 2 chemistry, so the one which is correct. So we've got to think about what we know about group 2 chemistry. So if we check number 2, it says barium is less vigorous than radium. If you look at group 2, we have beryllium, magnesium, calcium, strontium, barium, and radium. And we know that going down the group, their valence electrons are further away from the nucleus. In fact, the key idea is more shells Okay, so there are more filled electron shells, so they are further away, more shielded. If they are more shielded, therefore easier to remove. If they are easier to remove, that will make them more reactive metal, more reactive group 2 metal, especially in reacting with water, because metal, group 2 metal plus H2O, when they react with water, not steam, they will give you hydroxide as well as hydrogen gas. So there's just plus 2 H2O. So they become easier to do that. Barium reacts less vigorously. So barium is here. Oops, I don't want that. Barium is there. Barium is it reacts less vigorously than radium, and that's correct because radium is easier to lose the outer shell electrons in this redox reaction. This is a redox reaction because it is metal 0. This is group 2 metal, metal plus 2. Hydrogen 0 as an elemental hydrogen, which exists as a molecule. Hydrogen plus 1 oxidation state in water molecule. So that is option 2, which is correct because, barium is less vigorous with water than radium. Now to statement number 1. This is to do with solubility of the hydroxide. So as we know, going down the group 2, so if I just say the radius of the cation, this is the solubility of group 2 hydroxide. In AS, the candidates are expected to be able to state that the hydroxide become more soluble down group 2. If I imagine this as barium hydroxide, and of course, if I say that as barium hydroxide, usually I don't talk about radium hydroxide, but you can imagine that radium hydroxide would be even there. So even more soluble, because usually we just talk about magnesium hydroxide there, which is what you get when magnesium oxide, which is the oxide of period 3 in your case study under inorganic chemistry. It's going to be pH 9. Barium hydroxide is very soluble, and as a result of it, it's very alkaline, or you call it very basic, and therefore they will give you around pH 14. So which means this is even more basic because it's even more soluble than barium hydroxide, and that is what they're saying, barium hydroxide is less soluble than radium hydroxide. Statement 1 is actually correct. In terms of statement 3, this is solubility of group 2 sulfate. As we know, sulfate follows the opposite trend as the hydroxide. So you might have heard of what am I talking about? Barium sulfate. Barium sulfate is this very insoluble white PPT. It's your test for sulfate from O-level, IGCSE level. Paper 3 test for sulfate also appears in your paper 3 test for sulfate, also appears in your theory papers such as, well, this paper 1. Of course, then, radium sulfate will be even less soluble. We know that magnesium sulfate is only very, very, very slightly soluble, very slightly soluble. Of course, then barium sulfate is just much, much less soluble. Okay, so barium sulfate is more soluble than radium sulfate. More soluble is definitely correct. So far, we have gotten 1, 2, and 3 correct. So 1, 2, and 3 all are correct. So we're looking at option A as the possible, well, as the only answer for this question 35. Question 36, what we have is which statements are correct. So this is about oxides of third period. So oxides of period 3 element is part of an inorganic chemistry case study. Let me check number 2. They're looking at molecular formula, and they say phosphorus 5 oxide. So from the name itself, it would seem that this looks like what it is, but it's not the molecular formula. It's actually the empirical formula. This is actually not phosphorus plus 5 because these are both non-metals. So instead, what happened is they will share electrons. They will form covalent bonds instead of ionic bonds. So a lot of students forget about this from their very basic year 9 or IGCSE chemistry. So what happened then is P2O5, even though it's phosphorus plus 5 and oxygen minus 2, but oxidation number is assuming ionic character, which of course these are not ionic, these are covalent in terms of sharing electrons. So I'll show you this thing, which is actually P4O10. So what we have is O, O, and O like this. So that is P4O6. And what P4O10 does is the phosphorus is further doubly bonded to the oxygen, such that each phosphorus there will form 1, 2, 3, 4, 5 covalent bonds, and they become tetrahedral 109 degree, which each of the oxygen become 104.5 or 104 degree because they got 2 bond pairs and 2 lone pairs, whereas the phosphorus has got 4 bond pair because you only count the sigma bond, of which there's 1, 2, 3, and 4 there. Okay, so that is P4O10, and this is the molecular formula. Whereas if you want the empirical formula, then it's P2O5, which is empirical formula. Empirical formula is defined as the simplest ratio of atoms in the compound. So since option 2 is incorrect, so we are just looking at D as the only possible correct answer there. Okay, of course, then if you look at option 1 we already know is correct. SiO2 is obviously a giant molecular structure, which each silicon is bonded to 4 oxygen, and then each oxygen is bonded to 2 silicon, and then each silicon in turn is bonded to 3 other oxygen, just like that, and so on and so forth. This is giant covalent, or you call it giant molecular structure, as part of your structure and bonding, even from your O-level study. So SiO2 is giant molecular, giant covalent. This is simple molecular. So option 3 is wrong because silicon 4 oxide is not simple molecular. So up next, question 37. So which reagents could be used under suitable conditions? You're doing oxidation. So we're trying to oxidize CH3, CH2, CH2, OH. So this is 1, 2, and 3. CH3, CH2, CH2, OH. And we're trying to get to the aldehyde, which is this thing called 3-carbon aldehyde. The name is propanel. So make sure you know how to spell the correct spelling for aldehyde. This is propan-1-ol. It's not just propanol because you're in A level now. So essentially, to stop aldehyde, we need to heat and also distill immediately, because aldehyde does not form hydrogen bond between themselves, so no hydrogen bond. But this one has hydrogen bond between the molecules, so therefore this one will be higher boiling point. Whereas the one with the lower boiling point will boil first if you distill them immediately, which is why you get to isolate and also collect the aldehyde product. So the fact that you're doing oxidation, they have given you a couple of oxidizing agents there. If you look at option 2, potassium dichromate 6 is acidified. Without the acid, the redox will not work, as you have seen the equation from the data booklet. I always write the ion form instead of writing the K2Cr2O7. If you want to, you can write that. But from this ion form, I hope you can see that the charge of the ion is -2. You have 2 chromium plus 7 times -2 for the oxygen. And then you get 2 chromium equal to -2 plus 14. Chromium equal to plus 12 divided by 2. There's going to be plus 6. That's why it's called potassium dichromate bracket Vi, which stands for the oxidation number, chromium plus 6. This is orange in color. It will goes to green, which is chromium plus 3. Well, chromium plus 3 is the oxidation state. Chromium 3 plus aqueous is the final product as you go from this orange dichromate acidified to this green color species. 2 is definitely working as an oxidizing agent. 1 is your acidified MnO4 minus, or potassium manganate 7. So -1 manganese plus 4 times -2. Hopefully you can see manganese -1 plus 8. That's plus 7. So this is your purple color solution, which is manganese plus 7. From the MnO4 minus, manganese plus 7 will go to these colorless slash very, very pale pink cation in solution, which is Mn2 plus aqueous, and this is manganese plus 2. This is oxidation state. This is the species itself. This is the color of that species. Be very, very careful there. This is also oxidizing agent. What is not oxidized? Well, tolerance reagent is an oxidizing agent, but it's very specific. Can only oxidize aldehyde. And you are producing aldehyde. You are not oxidizing aldehyde. You are oxidizing alcohol. In fact, a primary alcohol. So this is option 3, and option 3 is wrong. So only option 1 and option 2 are correct. So we are looking at 1 and 2, which is B. Question 38, what do we have here? Which free radicals can be generated during a free radical substitution of chlorine and ethane? Okay, so ethane is 2 carbon. This chlorine, when they undergo the homolytic fission is the first step in generating the free radicals. So Cl2 in the presence of UV light will give you chlorine radicals, and 2 of them. This is called the initiation step in a free radical reaction. So in your propagation reaction, so for example, when you have propagation is when radical plus no radical will give you radical and no radical. So you will have radical on the left as well as on the right. Okay, so essentially this question is about all these alkyl radicals, which one is possible and which one is not possible. Looking through the options, I can tell you one is definitely impossible because one is a CH3 dot. Okay, so propagation, no way to cleave. To cleave means to break carbon of ethane. So cannot get one carbon radical. One carbon radical is that option 1 there, and if option 1 is wrong, well, therefore you must have option C, which is 2 and 3. Okay, so let me just prove to you that only 2 and 3 are correct. What can we do? We can have CH3, which is the chlorine radical plus the ethane molecule, and then you can take off one HCl because it take off one of the hydrogen and you will produce a radical on the carbon. So now you only have CH2 on the carbon and you have a radical on the carbon. And you can see that they want something which is CH2Cl, so there's a product. So CH3CH2 dot plus a Cl2 because radical plus radical will recombine in a termination, whereas I'm still doing propagation because in a theory paper they will say write a series of equations to show how you can get to the product or something like that. So the first substitution product will be from this propagation, not termination, I beg your pardon. However, we're trying to get to the next radical, and that next radical is the one with one chlorine already on it. So I can have CH3CH2Cl plus Cl dot, and now I'm happy with the CH2Cl on this side, which is the left hand side, option 2. I'll just take from there, and this is CH2CH2Cl like that, and I'll get HCl. Alright, so I get one of the H from there. I'm left with CH2. So this is actually your option 2, by the way, sorry, not option 1. And option 3 is basically you do from here, sorry, this goes to here, or if you go this way, then what else could happen is you could have am I correct? No, I am not correct. I am not correct at all. If this goes here, then this is what happened. If that go there, what am I doing? That was fine. Oh, what am I doing here? Okay, if I have CH3CH2Cl, if I choose to substitute there instead of on this end, then obviously you need to be able to write the equation to show the specific radical that you want. Okay, so CH and then Cl, and then I'll have dot and then plus HCl. Of course, it doesn't straight away give me the radical with the CH3. So I need to go further again. Oh, there's so many steps. CHCl dot plus Cl2, then I get CH3CH Cl2 plus Cl dot. And then it is the next step. It is the next step when this reacts with these, and then you will take out the H and you will get option 3 there. Okay, but of course option 3 requires the next radical production where this will take off the H and you'll get this particular radical on this carbon with 2 chlorine. I've just shown you a couple of steps, propagation steps, that could potentially lead you to option 2 and 3, but by right, if you think about option 1, one carbon means that you have to cut off or you have to cleave or you have to rupture or break the carbon-carbon single bond from ethane, and that just doesn't work in a free radical reaction. Okay, so you can form bond between carbon-carbon, but you don't break bond between carbon-carbon because there's a pretty strong bond to break. Option 1 is definitely incorrect, and that is why we already gotten the answer from the very beginning. I was just trying to show you if in a theory paper, you might be expected to actually explain or show in a series of steps how to get to a particular product via the radical being formed. Question 39, so you're looking for molecular formula C4H at all. So this is an exercise. This is an exercise of reading skeletal formula. I told you it's quite important to be able to read skeletal formula. The most important mantra is carbon form 4 bond. Let's check number 2 first. Carbon form 4 bond. So carbon form 4 bond is only show 1 carbon there. So there's 3 hydrogen there. 3 hydrogen. Carbon form 4 bond, so 1, 2, 3, so there's 1 hydrogen there. Carbon form 4 bond, this is the aldehyde, RCHO. So carbon form 4 bond, 1, 2, 3, so there's 1 hydrogen there, and there's 3 hydrogen there. So altogether you have 1, 2, 3, 4, C4, and then you have 3, 4, 5, plus 3 is 8, and you have 1 oxygen. 2 is correct. If you check for number 1, this is a ketone. The easiest way is this is a ketone, this is a 4 carbon ketone, no other functional group, and you know that ketone and aldehyde are in the same subtopic in your A-level syllabus because ketones and aldehydes are what you call functional group isomers. Okay, so ketones and aldehydes, they have the same number of carbons without any other functional groups. They are what you call structural isomers, specifically functional group isomers, which comes under structural isomers. Okay, so as you could see here, there are 4 carbon, so C4. There are 3 hydrogen because carbon form 4 bond, and there's, if I just write down, carbon form 4 bond, so there's 3 hydrogen. Carbon form 4 bond, so there's 2 hydrogen. Carbon form 4 bond, there's 3 hydrogen, so C4H at all there. So again, option 1 is correct there. If you look at number 3, number 3 is a very funny one. So this is not ketone or aldehyde, but instead it's got an alkene and an OH there. We're gonna have to do it manually now. When I say manually, I mean we just have to count, yeah? Carbon form 4 bond, you already show 2 there, so it has 2 hydrogen. Carbon form 4 bond, you already show 1, 2, and 3, so there's 1 hydrogen. Carbon form 4 bond, so 1 and 2, so you know there's 2 more hydrogen. Carbon form 4 bond, 2 hydrogen. Don't forget there's 1 hydrogen there. Altogether there are 4 carbon, 1, 2, 3, and 4. And then count the hydrogen, 2, 3, 4, 5, 6, 7, 8. So H8 and O. So again, we are looking for substances that have molecular formula C4H at O. 1, 2, and 3 are correct. So therefore, we're looking at option A as the answer there. We've reached the end of the paper 1. Finally, very long paper obviously. You want to form or you want to produce pentanoic acid. So pentanoic acid is a 5 carbon carboxylic acid. Okay, so if you look at option 2 first of all, so what do we have? If I convert that to skeletal formula, well actually I have an ester, so CH2, 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 and then CH3. If you look at this, CH3 or C double bond O, because it's CO, CH2, 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 that is your CH2 bracket 3, and then CH3, and then you plus HCl aqueous. So this is acid hydrolysis. Acid hydrolysis of esters is in your AS syllabus. And this is the ester bond that you break because this was the ester bond that you form when you form the ester. And guess what? You have 1, 2, 3, 4, 5. You're going to get carboxylic acid as a product because you are in acidic condition for your hydrolysis. Your other product being methanol. This is called methyl pentanoate because you named the ester from the alcohol bit first. Methyl pentanoate, you get methanol and you get pentanoic acid. So number 2 will give you pentanoic acid upon acid hydrolysis of the ester. If I look at number 1, number 1 is CH3, CH2, CH2, CHOH, and CH3. Let's just double check. CH3, CH2, CH2. Oh, I have got 1 extra carbon. That's no good. So let me start from that to 1, 2, 3, 1, 2, 3. So CH3, CH2, CH2, CHOH, CH3. and then you want to react that with H plus and MnO4 minus. Oh, okay, I think I can see what's going on now. 2 is definitely wrong because this is oxidizing agent. And then if you look at the alcohol there is green one. The alcohol there has a carbon with the OH bonded to 1 and 2 other carbon. This is a secondary alcohol because the carbon with the OH is bonded to 1 and 2 other carbon. Secondary alcohol get oxidized to ketone. So you can lose 1 hydrogen there because oxidation in the context of organic chemistry is loss of hydrogen, whereas the oxidizing agent itself will get reduced from the purple Mn plus 7 in the MnO4 minus acidified to give you Mn2 plus, which is an aqueous solution of Mn2 plus being colorless or pale pink. All right, so this is your ketone product. This is called pentane 2-on. So this is a ketone and this is not an acid. Number 1 is wrong. So 2 is correct, 1 is wrong. So therefore, you only left with option C, which is 2 and 3 are correct. Okay, so at this stage, you could have gotten the answer already, but let me just very quickly check option 3 just to prove my point that is actually correct. CH3, CH2, 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 and then Cn. 1, 2, 3, 4, 5. This is called pentane nitrile. So the 5 carbon include the important carbon there, C triple bond N, carbon sp hybridized, linear carbon for nitrile there. Okay, U plus H2SO4, this is acid hydrolysis again. Acid hydrolysis of nitriles, you are going to get carboxylic acid, which are 5 carbon like that. And don't forget that you're supposed to get NH3, but your NH3 is a gas, is a base that can react with the acid. So what you get is you get the salt, which is NH4 plus, and is ammonium sulfate as a salt. Because you are in acid hydrolysis, your base get neutralized to form a salt, and your acid, well, your carboxylic acid remains acid because you're in acid hydrolysis. So you do get 5 carbon acid. So we already said that the only correct answer where 2 is correct, 1 is wrong, so definitely option C. But of course we also check option 3 just because I'm doing a tutorial and I'm not doing an exam. But if you're doing an exam, you will have gotten the C just by looking at 2 first, and then 1 is wrong, so you have gotten this answer without even checking for this one. All right, so this is the end of this 40 question paper 1 tutorial, restructured format, not showing you question paper. Not sure how helpful that is, but I've tried to go through concepts in much greater detail that should hopefully help you with recapping or revising certain stuff from your AS syllabus. If you found that useful, do click the button on the bottom right, so bottom right hand side of each of my tutorial video. Subscribe to the channel and support my work, and share the channel widely with other people, like juniors, seniors from school, friends, chat group, relative, whoever else you think might benefit from this kind of full paper tutorials. And yeah, follow me at ptet.chemistry. That's ptet.chemistry on Facebook, Instagram, Twitter to get connected and to send in your questions or messages. All right, thank you for watching, and I'll see you in the next tutorial video.